Good morning, everybody. It's 9 o'clock here in San Diego, so we will begin. Welcome to this webinar on 3D molecular graphics, movies, documents, and presentations. The majority of this demonstration will be based on our free software that you can download from our website called ICM Browser. If you have any questions after the webinar, please feel free to contact me. My name is Andrew Ori. My email address and phone number is here. If you have any questions during the webinar, please feel free to use the questions panel in the GoToMeeting webinar panel on your computer. You can also follow Molsoft on Facebook, LinkedIn, Twitter, and YouTube. And at the end of this webinar, I'll provide a recording of the webinar. So the webinar topics for today are: we're going to read in 3D molecules from the protein data bank. We're going to annotate them, color them, and demonstrate how to change the representations. For example, ribbon and stick. We'll display binding pockets, active sites, colored by binding properties. Show you how to prepare publication quality molecular images, how to make fully interactive 3D slides, so you can build up a molecular, so you can make a representation of your molecule and save it as a slide, and then you can change that and can always come back to that same slide. And then how to import these slides into Windows, PowerPoint, and web pages, and also you can view them on your iPad or Android devices using iMoleView, which is a free download from Google Play and the Apple Store. And then show you how to make molecular movies based on the slides that you made or directly from a screenshot. So the software that we're using is ICM Browser, and it's a completely free download from molsoft.com/download.html. It's fully packaged for you. There's no compiling or anything like that. There's also Active ICM, which is also a free download. That's for PowerPoint and the web. iMoleView, which is for the Android and iPad, is available, as I mentioned, here. And there's only one thing I'm going to show today that's in ICM Browser Pro, which actually has a license fee, but it's a perpetual license. It never expires, and that's the movies. This software does have other tools, such as structure analysis tools and crystallographic analysis and electrostatic surfaces. So in this webinar, I'll be using a demonstration using kinases. So we're going to read in two ABL1 kinases, which are cytoplasmic and nuclear kinase. It's involved in cell division and adhesion, and it's a great drug target. In fact, Gleevec binds to this protein in the type 2 pocket. So you can see here we have the red, which is so this DFG region of the kinase, you probably know, moves in and out of the pocket. You can see the red pocket here is for DFG in, and when DFG moves out, shown here in blue, it opens up this extra space, so a larger molecule such as Gleevec can bind to it. And Gleevec is a drug for chronic myelogenous leukemia. So let's see what kind of information you can bring into ICM. You can read protein structures directly from the protein data bank, the PDB, or the Pocketome. The Pocketome is a database provided by UCSD, Ruben Abagayan's lab, It's an encyclopedia of conformational ensembles of druggable binding sites that have been identified from co-crystal structures in the PDB. Each pocketome entry describes a site on a protein surface that is involved in transient interactions with small molecules and peptides. So these two databases bring in 3D information. You can also bring in 2D chemical information from DrugBank, Chembl, and PubChem. So DrugBank is a resource that combines detailed drug information data with information such as sequence, structure, and pathway. So it's a useful tool. And Chembl is a publicly available database with more than 1.5 million compounds, small drug-like molecules. And the database is unique because it focuses on all aspects of drug discovery, and so you can relate the drug structure to the effect, the binding affinity, and other data. And then, of course, you have the sequence database UniProt, so you can read in sequences directly from UniProt. So let's go to ICM. So when you download ICM, you'll get an icon on your desktop. So you just double click it and you load an environment shown here. The search panel enables you to read in information from those databases which I mentioned. So we can search the PDB, for example. We can search like a string such as kinase, and this will show us all the kinase structures in the PDB. You can double click on an entry and that will read the PDB structure directly from here. And it's an ICM table, so you can have any data in here, but with ICM tables you can make plots. And so, for example, here we have a histogram of the number of kinase structures over the years that have been solved from 1976 through to today. So it's growing. So you can also search with a single PDB code from this search box here. So delete this. As I mentioned, you can also search the pocketome. So you go to pocketome. I'm just going to use one example, adrenergic receptor, and click here. This loads a table with all the adrenergic receptors in the PDB, in pocketome. So this is so if we click on one, for example, the transmembrane helical region of the beta-2 adrenergic receptor, this will display all the PDBs superimposed that are available for this protein. And they're superimposed around the ligand binding pocket. So you can see the pocket here, the ligand here in purple, magenta, and the side chains around. So it's a useful tool for docking. You can immediately read in all the PDB structures superimposed, and you can also visually see regions of flexibility in the pocket, for example, to look at. So that's the pocketome. You could also search directly the DrugBank, for example, or Chembl. So if we go to DrugBank, there's a button here which is a ring with a pencil on it. If you click on this, you could sketch a molecule that you want to search. But in this example, we're going to use Gleevec. So we use the chemical dictionary that we have here. Just type Gleevec. And it's sketched here. We have some property monitors here, but in the ICM Chemist, which is another product, you have more property monitors. And then it writes out the smile string, and we can do a search. And this shows us that the different targets for Gleevec that are in the drug bank. And we have the 2D structure here. And finally, the other kind of information that you might want to read in is sequence information. So we have the sequence for, we can look up the sequence from UniProt from, if we click on the drop down button here and choose UniProt and enter the UniProt ID. This downloads this sequence, this adrenergic beta 2 adrenergic receptor sequence. You can see the sequence here, and we can look at more information about it in this window here. So you can toggle on and off where there's mutations, where the disulfide bonds are. These are coloured here, and helical regions in transmembrane, for example. Okay. So we'll move back to the slides. So we're going to talk about colouring, annotation, and representation, and then how to build slides and also build, make publication quality images. So all the colouring, all the sort of colouring, annotation, and representation are involved in these 3 tabs on the top of the ICM browser. So you've got display, light, and labels tab, which are the main ones to manipulate images. We also support stereo, a variety of hardware stereo, but the most convenient and easiest to use are to get these $5 glasses and look at it in anaglyph stereo, and you can print out in anaglyph, or you can project in stereo, so people in your conference room or whatever can all wear these glasses and view in stereo for relatively cheaply. So I go back to the ICM browser, do a PDB search, and as I mentioned, we're going to be looking at Abel kinase. So this has as a code of 1 IEP. So you type the code in, and then ICM will download it from the PDB website, like this. So you can see that we have, I just prefer the white background. So to change the background color, we have this panel of colors. If you left click, it will color everything that color. If you right click, it will change the background. So I'm going to change the background to white using the right click. So we have rotation tools here. You can define a custom rotation if you wanted to around the x-axis by clicking and holding on this button. You can translate the molecule, zoom, and z-axis rotation, and also the 5% of the screen in the extremities of the screen are devoted to different actions. So you can see I have the cursor key here, but if I move it along to this region of the display, it turns into a zoom button. And likewise, I have a cursor, I move to the top, it turns into a Z rotation. And you can also use the button for translation. And the clipping planes, which I'll show, are on the right-hand side. So it's just a quick way of getting to these options. You can also add rocking motion using this button here. And you can change the direction of the rocking and the range of the rocking here. Okay. And so you'll notice that in the left-hand panel we have all the information that we need about this structure. And so we can toggle certain molecules on and off that we're not interested in. So you can see we have it's an X-ray structure, XR is for X-ray, it's 2.1 angstroms resolution. We have one protein chain, A protein chain, and a B molecule here. And these are all the molecules that are related to that A chain. So there's a chloride, there's 1, 2, 3, 4 chloride ions in that structure, along with a ligand, Gleevec. And in the B chain, it's the same. And at the end, we have all the water molecules grouped together here. So we may want to just make a clearer image of this structure. So I'm just going to remove all the labeling. So we can color this structure by any particular parameter. So it's displayed in ribbon. So you click and hold on the ribbon tab. You can say color by secondary structure. So green helices are red. And color by hydrophobicity. Probably for this example, it's better to color by molecule. So we see that we have the A chain is blue and the B chain is shown in yellow. So we might want to make a slide of this structure. So to do that, we click on this camera button at the bottom of the screen. You see that we have one slide. This means that if we change this image, we can always return directly back by double-clicking on the slide, back to our slide, and everything is saved. So if we had any annotation or any different coloring representations, then they would be saved. Okay, so we may just want to be interested in the ligand of the A subunit, which is the Gleevec bound to it. So we can display the ligand. The ligand is shown here, so we can just toggle the ligand on and off here. And we can zoom into the ligand by selecting it. To select something, we just double click on it here. And you see that the selection is in blue here and green crosses here. So now anything we do will be reacted to what is selected. So if we zoom, it's going to zoom in onto the ligand. It's going to try and get this in the right orientation. So yes, it's the kinase. We have the hinge region here, and we have the glycine-rich loop dipping down here, the N-terminal and C-terminal. So as I mentioned about the DFG region, in this DFG is out. So how can we find the DFG region? We can do that a number of different ways, but one way would be to look at the sequence of the A chain. By clicking here, we see the sequence. So you can search the sequence, so I know it's around this region, so I can find it here. Here's the DFG. So as I mentioned, anything you select this will respond to anything you select. So if I want to color it red, the DFG is here. If I want to display it in a stick, then stick here. If I want to label it, we go to the residue label button here, and the labels are the residue labels are there. So you can make another slide of this, for example, show DFG out. And then we can toggle between the two slides that we've made. Just to show you some other coloring, which is sometimes useful. So the ligand, we might not be happy with this yellowish color for the carbons. We can change the coloring of the carbons. So we need to select the ligand again. And then you can see that these buttons show you what representation this ligand is in. It's not in wire, it's in stick, it's colored blue. So we can change the color of the stick by clicking down on it and going color by, and then you can say color C only, and we can choose a color that we like, and that colors all the carbons green. We could select the sticks and display in CPK, transparent CPK, and other things like that. So if you click and hold, you get a variety of different options. You can change things like thickness and other options, the style of the chemistry, representation. So let me return that back to. So you could maybe remove these the ends of the ratio ball of the stick will be 1, so it's nice and flat. But it's up to you. You can save these preferences to how you like it. Okay, so we may also be interested in the residues surrounding this ligand. So a way to do that is to select them, to right-click, and we choose color and select. You right-click on the ligand. We can choose neighbors, and we can say we want to see all the residues within 6 angstroms of the ligand. Go OK. And you see we have green crosses here. You can see exactly which residues are selected in the sequence here as well. And there's a button here which says R. So this propagates. So if you make a 6 angstrom selection, you may not select every single atom of the residue. So you want to make sure, if you want to display the whole side chains, you can propagate that selection to all residue, all atoms of the selection that you made. And so we have all the side chains here. And we can color the side chains by molecule carbon. So you can see they're the same color as the ribbon. So maybe we like this image. We can save it as another slide. So when you make slides, you can also change the transition between the slides, which will be useful when we come on to making movies and also documents. So you can have smooth, if you right-click on a slide in the ICM workspace, you can edit the slide and add a transition effect, for example, and a blend transition like this. Okay, so now if we toggle through the slides, we get a bit of different effects like that. Okay, and also if we like this picture, we can save it as a, maybe this one might be more useful. We can save it as an image. We can click on this button here. If you click it once, it will copy the image to clipboard. It's quite a big one for the structure, but you can also write the image out if it's too big, like that was. That'll write it into a file. You can see it's written out one PNG image. Or you can be more specific in how you want to write out the image. If you go to Write Image Advanced, you can change the size. You can have a transparent background. You can save it as PNG or JPEG or any other, quite a few other formats. It will just react to whatever file name you give it. So if you want JPEG, you put JPG here. And so that's advanced. You can also add image to an album, which is sometimes useful for molecular documents. So you can add this to the album. So we have this now in the ICM workspace saved. And you can also set it as a background image as well, which is sometimes helpful if you're comparing structures. Okay. So now we're sort of moving on to the pocket. We can display a variety of different ways of representing the pocket. One of them is the receptor surface. So it's showing you the binding properties of the receptor surface. So red is hydrogen bond acceptor and blue is hydrogen bond donor. White is neutral and green is hydrophobic. And then another way of representing the pocket, which gives a better way of seeing cavities where you may want to build out of, when you can see dead ends quite easily, is called a ligand surface. It's sort of a combination between the receptor surface and the surface of the ligand, a sort of subtraction of those two. And we'll see that example here. So to do that, to show the pocket of this ligand, just going to run this way. So we have one ligand here. To show the pocket, we can right-click, choose pocket, and choose receptor pocket. If we do that now, it will just give us a generic sort of whitish pocket. And the reason for this is that this is a raw PDB. There's no hydrogens added, and there's the particular side chains haven't been optimized for the hydrogen bonding network, so there's no way ICM can accurately predict or calculate the binding properties for this pocket. So all we need to do is convert this X-ray structure. We need to add hydrogens to it. So we can do that by right-clicking on the object here, choose Convert PDB, and we can choose delete waters, keep tight waters, or keep all waters. Just for this example, I'm going to delete them. And then you can optimize certain residues where there may be ambiguity about the position of the side chain from the crystallographer's point of view, because we want to optimize the hydrogen bonding network, so we can rotate asparagines and glutamines, for example. Just for this example, I'm not going to do that because it takes a little bit longer. You can optimize all the hydrogens. I'm going to overwrite my original X-ray structure. And so in some cases, if you have a low resolution structure, some of the side chains may be missing atoms. So you can, by default, if you uncheck this, ICM will build those missing atoms based on the residue type, or you can just hide them and ICM will flag that there's actually, the crystallographer didn't see this atom in this position. And just go OK. This is converting that PDB into an ICM object. So it's adding hydrogens, and now we should be able to build the pocket. So we right click and say pocket, receptor pocket. Just as an example, we'll display the hydrogen bonds and labels and go OK. So the pocket's displayed. This is the receptor pocket, colored. You can see that this is the hinge region here, and the pocket extends further away out towards the alpha C because the DFG has moved out. If you're doing this at home and you're using the very latest version of ICM, there's a very small bug we found yesterday for the convert protein. So I will send you the link, and that will fix it. We made a slight modification, and that screwed things up. And there's another question about figures. I might have to get back to you on that later on. So this is the crystal structure, and the pocket is displayed here. We can also display the other alternative pocket. If you right-click on the pocket and you choose ligand surface, this provides the other kind of surface which I showed in that slide. And it takes a little bit longer to build, but it's a very useful representation. So this is the pocket. So you can see here that it's sort of closed off, so there's very little space there. So you wouldn't be, if you were thinking about ways of modifying this ligand, there wouldn't be any. If you want to keep the same pose, there wouldn't be any point in trying any modification at this point here. And likewise here, obviously towards the hinge, you're sort of stuck as well. But you can see in this example that there's an opening here in this region, but in actual fact that's sort of going out towards the water. But it gives you an example. So if you got if you're using this for drug design and using maybe your own chemical intuition, and you want to try and build off this structure, it's a useful representation. So now we've added hydrogens, we also have can display the hydrogen bonds. So, and you can see we have a hydrogen bond here. The coloured green it's probably not very well optimized, because when I converted it, I didn't optimize the hydrogen bond hydrogen. So this would probably be improved. This is a reasonable hydrogen bond in terms of the distance and the angle, and so it's in green. Strong hydrogen bonds are in blue, and weak ones are shown in red. And you can toggle hydrogen bonds on and off here in the display tab using this button. And also you have another part here in the 3D labels, so you can toggle individual ones off. So this one is here. So we can toggle it on and off. We can change the wire representation, or you can add the distance, 2.9 angstroms. You can change it whichever way you want to here. So you can also set your own hydrogen bonds by making a selection and then clicking on this button shown here. Okay, so we're going to finally read in another PDB, another ABL kinase from the PDB, and that has a PDB code of 1 OPK. Okay. So now we have, just going to clean this up. You can minimize how much information you see using these plus and minus. So this is another ABL1 kinase, and it only has one protein chain. It has a ligand bound to the ATP pocket in the type 1 conformation. So it'd be nice to compare the type 1 pocket with the type 2 pocket. This also has a long N terminal, which I'm sure it's very useful, but I don't like it. It gets in the way of the images, so I'm just going to undisplay it. Here. So now you can see that we have the glycine-rich loop and the hinge region. So we can and we also have our original type 2 kinase here, the blue one. So it'd be nice to superimpose these two structures. So to do that, it's very straightforward. You can use these selection tools and make a rectangular selection to select both. And then you just click on the display tab, and there's a superimpose button here. And it asks you which object you want static, and we want the original one, 1 IAP, to be static, and go OK. You can see now the two kinase domains are superimposed here. The superimpose button is just going to undisplay some of it's very easy to use, very dynamic. So if you wanted to maybe just superimpose this loop region from the beta 3 to the alpha C, you can just select that region and press the superimpose button, and then that loop will be superimposed. So basically it works on any selection you make. So I'm just going to remake the selection. Sometimes it's useful to superimpose just around the binding pocket. So you can display the ligand, make a selection, select neighbors, and then just superimpose. If you want to be more specific about your superposition, you can go to Tools and then Superimpose, and you can change, if you want to do just superimpose backbone atoms, for example, proteins by 3D match by sequence, or by just the alphas, or whatever you want to do. You can, the question about the superposition, you can export a transformation matrix, but I'm going to have to show that. Maybe I'll send you an email on how to see that. Can you superimpose two proteins with the same ligand doing that? Yeah, you can superimpose basically anything you want to. Color by object too. Yeah, it's not based on the ligand or anything like that. So you can just you can superimpose basically anything. Okay, so we have the two structures. Now it'd be nice to just compare the type 1 and type 2 pockets. So we already have this is the type 2 pocket. I was going to display it, if you right click on a surface, you can color uniform. I'm going to type 2 will be red, and the pocket for the type 1 is obviously going to be smaller. It's got a ligand. It's going to undisplay that one. So the ligand is here, just purely in the ATP binding region. And so when we display the pocket for this, it's smaller. We can color this one green. So now we can just compare. It's quite obvious. You can see that when the DFG moves out, you get this extra volume in order to build a specific inhibitor. Okay, so that we built the slides. We can export those slides to a movie if we wanted to. This is the only thing that I've shown that's not in the browser. So you can right-click on the slideshow here and choose. This is an ICM Browser Pro, so you export as movie, and you can determine. You can set smooth transitions, blending, and other things. A number of frames between slides. You can also add rocking. However you want. There's also another. Let me just do that. So export as movie. Go OK. There's also another screenshot movie here, which basically records everything you do in the graphical display. So if you zoom in, it will record it. If you zoom out, it will record it. But I find that doing it by slideshow, it's more specific, and you can go directly to the the images that you really want in a smooth way. So that's writing out the movie. While it's doing that, it takes a little bit of time. We'll carry on with the presentation. So, ligand binding pocket. Now we're moving on to graphical effects. One particular effect which is pretty useful is called, the movie is taking over. It's called Moleskin. So it's very useful for showing protein-protein interaction sites or ligand interaction sites. The molecular surfaces are generated with assigned colors and occlusion shaded. The carbons of each molecule are colored by its own consistent color. They're labeled, and the patches are brought to the front. So you can see the interactions pretty well. You can see that. So we have an example of this. The movie is written out, but let's quickly view that. It's a standard MPEG-4 movie. Maybe I'll show it later on. But so we go to. I'm just going to read a new session just for this graphical effects part. So the structure, we're moving on from kinases to proteases now. So the structure that I'm interested in is 2-SNI. It's a cetylysin protease. So it initiates like a nucleophilic attack on a peptide amide, and there's a serine residue here which does it. And in this structure we have a nice protease inhibitor. So we can color those in. We'll just display the molecules different colors by color by molecule. So the inhibitor is in yellow, the protease is in blue. It's going to undisplay sticks and CPK. So it'd be nice to see how this inhibitor interacts and see if it hits the serine in the serine region that initiates the nucleophilic attack. So to do this, we'll right-click on the object. So any right-click option or these drop-down buttons, they only respond to whatever you've do it on. So if you right-click here, it will only respond to the E subunit. But I want to do it for everything, so it's the whole object. So it's 2-SNI. You may have noticed I've been clicking these buttons here as well. I should have mentioned when we're making images. These toggle high-quality image. and it also has anti-aliasing option. So whenever you make an image, you really should toggle these buttons. So we're going to look at the skin. We go to Shapes, Make, Molecular Shapes and Contacts, Build Surfaces and Color by Contact. Go OK. So it's making the surface, looking at the contacts, and now we have a table telling us that the subtilisin is in sky blue, the inhibitor is in yellow, and so we can remove this. This is this one, I think. And so if we remove that, we can see the colouring of the receptor here. If we undisplay this molecule, see the serine in the catalytic site here. And so that is what we call mole skin, or conveniently changed names to shapes. And so you can also change the color here by you can color the surface by atom selection. So if you make a selection of the active site, you can color it yourself, or by proximity to selection. So the next graphic effect we can look at is a fog effect. It's pretty straightforward. The fog is turned on using this button called fog. So to select it, and you can then change using these yellow buttons are clipping plane, so you can add more fog to the background by using the back clipping plane. You can clear all clipping planes here, so back to there's no fog. Or you can also use the front as well, so you can actually cut away the fog, the front. Transparency, as I mentioned, anything to do with a particular representation. If you click and hold, you get the options in the display button. So you make it transparent, and like that. Sketch accents is sometimes nice. It just gives go to Tools, so Edit, so View, and then go to Sketch Accents, and that will add this sort of outline around the outside of the molecules. Let's just suppose it's transparent. So you can toggle that on and off here. Graphic shadows. So shadow button is here. It's quite tough on the graphics card when you add this. So be careful if you have used it. Rotation might get a little bit slow. It depends on your graphics card. Okay. So you can see a few shadows down here. You can go to the lighting tab and you can change the direction of the light source. So that would change the obviously it's sometimes useful for nice images. You can play around here. You can also change the shine here in the light tab, and different variety of different things. And I might want to go back to the default, and you can click here to do that. Okay, occlusion shading. We have, these are the surfaces here. They've got G underscore represents surface. So you can change the occlusion shading. So this gives a better representation of how deep a pocket might be. so it gives it a more shading. You can change it by right-clicking on the surface and going to occlusion shading. And also you can make directly other surfaces. We made them using shapes, but you can also go to meshes, and in Browser Pro you have the option for electrostatics, but you can add other default surfaces here as well. Okay, just quickly while we're on surfaces, so we have this structure displayed in stick. We have the surface on it. How we can cut away the surface using the clipping tools here. You can see the structure underneath, but you notice that we're clipping the surface plus the wire underneath. So it might be nice to not do that and just clip the surface and leave the wire hanging outside. So to do that, there's a button here called Clip Skin Meshes. If you select it, then if you cut away now, you see that it's not cutting away the actual representation of the structure, the wire. It's just cutting away the skin. If you make a nice cut and you want to lock it, so basically now if I rotate, it's going to make that same plane cut through the molecule wherever I rotate. But it might be nice to lock it at this point. Click a lock button here, and then so if we rotate it, we can show it in this representation. Okay, so that is the graphics effects tools, and then finally, I'm going to move on to the Active ICM. So Active ICM is a free download, which is useful with ICM browser. So you can basically put into a single file, you can add images, sequences, plots, and other information. You can put this into a single file in HTML format, and these can be directly linked by hyperlink to 3D structures or tables or any other object you have in ICM. And this is packaged in one convenient file, and then you can view this file in ICM browser or on a web page or in or in Office, Microsoft Office. This was developed in conjunction with the Structural Genomics Consortium in the University of Oxford, Brian Marsden's group there, and Ruben Abagayan here at Molsoft and UCSD. And it was developed primarily because the SGC was solving lots of structures and they wanted to quickly find a way of presenting these structures to the general public without publishing them. But after a while, certain journals got interested, and there were quite a few papers in PLOS ONE and some in these other journals where the scientists have used a fully interactive 3D session to publish their work. And I should mention now that it's an old slide from 2009, but we now have this IML view, and so you can view your molecular documents in IML view, which is actually now for Android as well. So that's free. In the Apple and iPad version, there's also a $1 version, but it's not a lot of difference. You may as well get the free version. So how to make these? So as I mentioned, we made this slideshow before, all about our Gleevec and type 1, type 2 pockets. That's the DFG. So we can annotate this this file. We go File, New, and build an HTML panel here, and we can edit this panel. So this is basically brings up a sort of Word document, environment to type and add things. So we can say a global view of 1 kinase type 2 pocket. Type 2. We can just add a link to a slide. So we select the text, click on the slide button, and add a slide. You can also say, I think any text. You can add headings and checkboxes, links to web pages. You can add images and other things. But I'm just showing the slides. Detailed view of Pocket or DFG out is shown, and detailed view of Gleevec Pocket. And so we can add hyperlink again for slide number 2. And sorry, let's just separate. So make a selection here, slide number 2, go OK, and slide 3. Okay. We can save this as so we can save what we've done, save in editing. So now if we click on these links, it will take us to the to the DFG, to our original structure, and to the Gleevec Pocket. Okay, so we can export this into there's a few questions. I'll probably try and answer those at the end. Thanks very much for the questions. I'll get back to you. So we can now export this. We can save this as an ICB file, which is our binary thing. So you can save this and send it to your colleague. He can read it in ICM browser or iPad. We can export it as HTML. And just like this. We're also, very soon, we're going to have a new way of using JavaScript to do this. It's coming very soon, but I can't show that yet because it's not fully implemented. And we go OK. And this will export it to HTML. So it writes it to the most likely to documents file here. I double click here and open it up in Firefox here, and we see that we have the Active ICM, and this is in the web browser. So now we can toggle through the slides same way. DFG out, Gleevec Pocket, toggle here. You can make selections as well, and there's a few other tools if you click on the button here. Okay, so also sometimes it's useful to put it into a PowerPoint presentation. So you need to download Active ICM to do this. Just need another PowerPoint session here. And if you've downloaded this if you download Active ICM, you go to the developer ribbon, and you'll see this button here, and you will see Active ICM class. Click on that, go OK. Define the size of how you want to import it, and then choose the ICB file format. What we've done, and yeah, it's in there. So now we can just go to, and it only becomes active when it's in slideshow mode. So go to slideshow from beginning, and then this is fully interactive in PowerPoint. So you can toggle like in the browser to your individual slides. You also got options here if you click on the button here. Okay. So if you missed anything, I'll send out the recording of this webinar, so you can maybe follow along, slow it down a bit. Thank you very much for your attention, and I will answer some questions in a few minutes. So the next webinar is on linking protein structure sequences and alignments to protein structure. This is in a product called ICM Bio, which is a pretty low-cost product. And basically, you can make alignments, and these alignments are directly linked to protein structure. So you can select in the alignment, and that will propagate to your 3D structure. And likewise, you can select here. So it's useful for coloring and investigating structures and comparing very large alignments and a wide range. There's also blast searching and other tools available. Yes, so thank you very much for your time. I'll be here for the next few minutes or so to answer any questions. And if you have a question, you can put your hand up and I can let you answer it via audio or through text through the questions. So we had a question about scripting. So everything I showed here can be scripted. And so we have this terminal window at the bottom. So for example, so you can read PDB and everything, basically everything you've done, I've shown. So I can send you the links to the scripting. We have a whole separate workshop on scripting, but a good way of learning the scripting is to sort of you can do the actions in the graphics and then see what comes out in the terminal display. So everything that's done in the graphics is dumped here. So I displayed CPK as AS_graph is a selection. So if you make a selection here, if you type res AS_graph, you can see all the residues that have been selected. Or you can say something like string res AS_graph, and then you can see directly the residues here. Everything is fully interactive. Yes, everything. The tools menu. Some of these options only become active in the Pro version. For example, as I mentioned, the X-ray crystallography, 3D prediction. So basically, everything I showed, you should be able to do apart from the movies, unless you have ICM Browser Pro, which is an addition to that. As I mentioned at the start, we had a very small bug in the very latest version, which we fixed, and I'll send you the new link with the follow-up email along with the video. But Mac version and Windows version and Linux are exactly the same. You should see the layout, but in the Pro version, I don't think you see the tools button. Had a question: does it read trajectory files? We have our own ICM trajectory files, but we just started to. We had a request a few weeks ago, and so we now support GROMAC's trajectory files. If there's another format you're interested in, maybe could send it to us, and we could probably look into speak to developers and see if we can support it. We'd have to have the very latest version to read the GROMAC's one. Yeah, so charm. Okay, we'll look into the charm trajectories and make a note of that. Great. So there are other tools that I didn't show, for example, 2D labels you can add as well here. I should mention, if you want to try the Pro version, that's fine. I can send you a trial license, evaluation license for a month, and you can use it. For the GROMAC trajectory, you have to have maybe yesterday's version of the development version. We only just, Max Totroff just recently developed, incorporated it, so I will send that out. It's still kind of in development because we have a way of viewing a stack of confirmations, and I think it's maybe have to wait a couple of weeks really to get it needs to be tested, but should be available soon. I had a question about displaying interactions. So mainly the interactions you see in 3D are the hydrogen bonds, and we haven't ever sort of included any direct way of showing the pi-pi interactions or pi-cation interactions, but that might be a useful addition. But yeah, obviously you can do it visually, but it'd be nice to maybe highlight them to show them. Had a question about the optimal size for particular figures. I will send out a link which requires the command line to maybe interact with. So basically, for high quality images, you need these selected, and then you can this anti-aliasing and here. But to define a number of dots per pixel resolution and stuff, you need to. I send that out. Yeah, that's a nice question. Can you export the Pocket mesh as a volume file? Yes, you can. So at the moment, this mesh, we have a mesh here. It's like this mesh is connected to this protein, so we'd have to move it out. So right-click and say unlink mesh. But once it's exported, you can it comes after that. You can save as, and you can choose object file. .obj format or STL format for 3D printing, and this other 3D format here. Yeah, the Pocket mesh equals Pocket, but you can also have a mesh for anything really. So we can make a mesh for something small. I'm just going to pick the ligand. We could say go to meshes and choose. Imagine this the protein, just a plain solid, and it'll make a plain solid of the surface of this ligand like that. Yeah, we have sort of interchangeable terms. So we have mesh, pocket, or grobs, graphical objects. They're all basically the same objects really, and they all have this G underscore prefix, so we can remove this, unlink, it will move it into this section of meshes. And there's meshes, if you right click, as with most things, you can color by different, or you can change, you can cut them, crop them, or whatever. I'll send a link on how to get the transformation matrix as well in the follow-up email. Great. So I don't think there are any more questions as far as I can see, but if you have any questions, please feel free to email me, and please join us next, I think it's next week, next week for the ICM bio. Thanks very much for your time.